Hi, everyone. This is Mark. I just wanted to offer a quick, almost Dr. Zoc style, rapid review of some biostats concepts. Just from noticing that Amboss's practice step one said that step one's going to emphasize biostats and humanities a little bit more heavily this year. And that I think just reviewing this stuff is helpful. The way UWorld asks these questions is always super confusing. And so just in case step one does the same thing, I wanted to give you guys some additional tools to think about some of these concepts that we've learned beyond what we covered in the curriculum. So I wanted to just try this out with sensitivity, specificity, and the 2x2 tables. And if it's helpful, maybe I'll cover some other stuff as time allows. So let's get started. To begin, we'll just go over some quick definitions. Prevalence is the total number of cases per unit population. Incidence is the number of new cases, usually per year, per unit of population. Sensitivity, which you can also call the detection rate, is the probability of a positive result given the patient has the disease, but can also rule things out, which is kind of confusing. And then specificity is the probability of a negative result given the patient does not have the disease, but also rules things in. So specificity is about negative results, but you trust the positives, and that's confusing to me. We're going to get into why that works that way. Positive predictive value is the probability of having the disease given a positive test. Negative predictive value is the probability of not having the disease given a negative test. So we're going to get into what given means, and we're going to talk about that using the way that I learned probability, and probably a lot of you learned probability, which is with marbles. This is a jar of marbles. It's got 20 total, 10 greens, 7 reds, 3 blues. So if I ask you what's the probability of pulling a blue, I bet you can all tell me. It's 3 over 20. It's 15%. If I ask you for the probability of pulling a blue, given that you are not pulling a green, so if I tell you you're guaranteed not to pull a green, then what's going to happen? Well, I want you to eliminate those 10 greens from the denominator. Now you can only get a red or a blue. So your denominator is 7 plus 3, and that means your probability is 3 over 10, or 30%. That is how we think about givens. Is given kind of becomes your denominator that you then pull the probability from. So it's as if you pulled all the greens from the jar of marbles. That brings us to our classic 2x2 table. True positives, false negatives, true negatives. You guys have all seen a bunch of these. And so we can calculate a lot of things from this. One is the prevalence, the total number of cases per unit of the population. If we assume that this table contains everyone in the population, then take a second and think about it and tell me what the prevalence is. That's exactly right. It's everybody with the disease, so in this column, divided by the total population. So that's true positives plus false negatives divided by n, which is just statistical shorthand for the full population always. So that would be, you could also think about that as true positives plus false negatives plus false positives plus true negatives. Incidence, the number of new cases per unit of the population. How would we calculate that with this table? So that's actually a trick question. You can't get that from this table. You would need some kind of line graph or chart that shows you the number of cases per year, and that would help you get the incidence. So now let's talk about sensitivity. Probability of a positive result given that the patient has the disease. So we talked with the marble example about the givens. And if we're given that the patient has the disease, that means it has to be either a true positive or a false negative. It has to be in this column. And so that becomes your denominator. So take a second. Given that the patient has the disease, what's the probability of a positive result using this table? That's exactly right. It's true positives divided by true positive plus false negative. Specificity is very similar. It's just kind of on the opposite side of the table. Probability of a negative result given that the patient does not have the disease. Take a second to think about it. That's exactly right. It's the true negatives divided by the false positives plus the true negatives. Because if we're given that the patient does not have the disease, they can only be a false positive or a true negative. That's all it can be. So that becomes our denominator. If people with the disease are green marbles, all the green marbles are gone. It's false positives plus true negatives, and so all the true negatives are taken out of that. How about the positive predictive value, the probability of having the disease given a positive test? So we switched it up a little bit. Now our denominator is going to be positive tests. So it's true positives plus false positives. So it's just true positives divided by true positives plus false positives. This is the number that your patient is going to care about the most, right? They're going to want to know, okay, I got this positive test. How likely is it that I actually have cancer or whatever else? And just for sake of completion, negative predictive value, take a second. How would you calculate that from this table given that definition of probability of not having the disease given a negative test? Got it again. It's the true negatives divided by true negatives plus false negatives, because if we're given a negative test, that means we have to be in this row of the table, and so this is what we get. And as we think about this, I think it can be kind of confusing. Why does sensitivity, which has to do with positive results to calculate it, right? Why does that rule things out? And that's where I want you guys to think about something that I don't remember ever talking about in class called the false negative rate. The false negative rate is the probability of a negative test given that the patient has the disease. It is false negatives divided by true positives plus false negatives. And in that sense, it is also the converse of sensitivity. It is 1 minus sensitivity, right? Because if you imagine true positives over TP plus FN plus false negatives over TP plus FN, if you guys remember from fraction addition, if the denominators are the same, you just add the tops. And so true positives plus false negatives is true positives plus false negatives. So it's the same as 1 minus sensitivity, which means, in other words, as sensitivity gets higher, the false negative rate has to get lower because the false negative rate plus the sensitivity has to add up to 1. And so that's why it's really helpful. And so I've created this little table here, and we're going to look at the sensitivity. So it's the true positives divided by true positives plus false negatives. So right now, the sensitivity of this test is 80%. Which means that the false negative rate is here with the same denominator. And, plus this guy right here. Nope. 4. And you will notice that the sensitivity plus the false negative rate is equal to 1. And that always has to be true. And so if we change the number of false negatives, you can see that as I adjust it, the number of false negatives goes down. The sensitivity increases and the false negative rate decreases, but they always are going to add up to exactly 1. And so as the number of false negatives continues to plummet, that sensitivity gets higher and higher and higher and higher and higher. And so if something is, let's say, 98% sensitive, you can see it's got a false negative rate of just under 2%. False negatives are really rare. That is why a sensitive test means that you can trust a negative result, because you are forcibly making that false negative rate low. Specificity is the same thing in reverse. We move over to this side of the table. True negatives divided by true negatives plus false positives. So I want you guys to think about the false positive rate. Take a second and think about how you would calculate that. That's exactly right. It's going to be the false positives divided by false positives plus true negatives. And so this, again, will be the converse of specificity. It's 1 minus specificity. They always have to add up to 1. And that means as specificity gets higher, the false positive rate has to get lower. And so if we look at the same example on this side, we're just going to real quickly key this in. And the false positive rate is the false positives divided by, right here. And we see that they sum again to 1. And so the specificity of this test currently is really high. It's 98%, which means the false positive rate is super duper low. But if we increase the number of false positives, and you can see it ticking up, that specificity starts to go down. And at an even rate, the false positive rate starts to go up. So the higher the specificity, the lower the false positive rate, and vice versa. As the specificity drops, the false positive rate gets gets higher and higher and higher. And that is why a specific test can rule things in, because if the test has a very high specificity, if we move this down here, it has a very low false positive rate. Hope that makes sense. So in summary, sensitive tests rule things in because of that low false negative rate, and specific tests rule things out because of that low false positive rate. Another thing that's really important to understand, and I think I remember Dr. Walters talking about this, sensitivity and specificity are properties of the test. Positive and negative predictive values are properties for the patient, right? You're going to get a positive or a negative test, and that will inform you how likely is this patient to have the disease. And so if you guys like this and decide that we want to do more, and my schedule allows for that, that'll be what I cover next time. What does it mean for the positive and negative predictive values to be properties for the patient, and how can we determine the overall accuracy of a test? I think we'll get into things like diagnostic odds ratios, ROC curves, all sorts of fun things like that. I hope this was helpful. Please email me or group me or text me if you have any questions, and let me know if you're interested in more. Thanks. Have a good night.